Last day we talked about the concept of work. Now I gotta be honest, work and energy, kids usually do pretty well on because it's a scalar, no trig. Okay? But some of the difficulties are, in your unique case, this would already have been a review lesson for you because I would have normally covered this after spring break last year. Didn't get to it, sorry, Karin, with COVID. Okay. But also because the words in this unit, specifically work and energy and power, have English meanings that have very little to do with physics meanings. When you say, I'm doing work, you mean you're getting tired. By the way, tiredness is power in physics, not work. When you say, I got power, you mean, I'm feeling strong. No. Actually, if you're generating a lot of power, that's what's making you tired. And energy has a very specific definition. So we said last day that work, you're going to end up today with 3 definitions of work. Okay? The first is that work is force times distance. That's the simplest definition, but there's conditions. It has to be a constant force, and it has to be in the same direction. The force and the distance have to be in the same direction. So it's very limited. As an example, we can't use work equals force times distance for going into outer space, because as you leave the Earth, as you get further from the Earth, what happens to the force of gravity? Changing force, I can't use work for outer space stuff. I can't use force times distance. I'll have to give you a better, yuckier, but far more flexible definition of work. We did a little proof to show you that work is a scalar. We looked at 2 situations. We said that you could figure out how much work to lift something straight up. Then we figured out how much work to push it to the same height up a ramp, got the same answer. And we said, doesn't matter how you get there. In fact, that ramp question, if I gave you a 5-meter ramp and the ramp looked like this, all work cares about is where did you start? Where did you finish? That's how much work. It doesn't care at all about the path in between because it's a scalar, which is nice. I did tell you you can have negative work, and you're going to see later today, negative work when the force is in the opposite direction of motion. Sean, that means you're losing energy, not gaining energy. And then we did 1 trig example. I said technically work is force times distance cos theta, but I told you all that theta is either going to be 0 or 180 degrees. Aiden, that's a long blink. You going to make it? You sure now? Oh, it's on. It's on. People on YouTube, what was that rattling sound? My Nerf dart gun. Okay. First definition of work, work is force times distance. Second definition of work, it's also the area underneath a force versus distance graph. How will you know to use that method? Captain Obvious, they're going to give you a force versus distance graph. Okay? And so we looked at how much work was done in moving an object from 2 meters to 6 meters. It was the area of this trapezoid. Oh, we said that you don't need the formula for the area of a trapezoid. Any trapezoid can be broken into a triangle and a rectangle. Add them up. Energy is the ability, energy is the ability to do work. In other words, if an object has energy, it can apply a force over a distance. That's the definition for energy. Again, when you say, I'm feeling energetic, what you really mean is you're wide awake and alert, the opposite of Aiden, okay? That's not what it means in physics. Energy very specifically means an object has the ability to apply a force over a distance. We talked about different types of energy. The main 2 we're going to look at are kinetic energy, a half mv squared. That's on your formula sheet. You might want your formula sheet out, by the way. And stored energy, potential energy due to gravity, mgh. And then we got to the work-energy theorem. This is the point of the lesson. Work is what times what? Who remembers? That's the first definition of work. That's the nicest and the easiest and the most convenient, but also the most limited. Only works for constant force, same direction. Work is also the area under a force versus distance graph. Little more, no pun intended, work to do, a little tougher to do, but okay, it'll be obvious because they'll give you a force versus distance graph. But when the force is not constant, we have something called the work-energy theorem. This is the best definition of work. It's also, no pun intended, the most work. When we look at orbital mechanics and we calculate how much work to put something in orbit, it'll be about 15 lines. It'll take up an entire page. It'll be the single longest question of the entire year. The net work on an object is equal to its total change in energy. What? Work is equal to the change in potential plus the change in kinetic energy. I think I put that on your formula sheet. I used to not, but I think I added the work-energy theorem to your formula sheet. Did I not? He's asking. That's also my way of saying, please know where we are now on the sheet, okay? Some textbooks give a modified version of the work-energy theorem. If the object isn't changing height, you're neither gaining nor losing potential energy, and so they'll tell you that the amount of work is just equal to the change in kinetic energy. That only works if you're on a flat surface. The more useful definition of work is it's the change in potential plus the change in kinetic. Put your pencils down, look up. I like example 8, I like example 8, I like example 8. Example 8 is a nice question. I want to show you how I handle example 8. Aiden, can you read example 8 to me, please? Stop. How much what? Work. See, my first thought, don't write this down. My first thought would be, well, work equals force times distance. Don't write that down. Read the question, Aiden. Do you see a force in newtons anywhere? Do you see a distance in meters anywhere? Do you see any easy way to find a force? I don't see an accelerator. I see a mass, but I don't see much else. I kind of see stop. My next option for work would be, it's also the area under a force versus distance graph. Captain Obvious, did they give you a graph? No, so I wouldn't use that. So I will go to my third, more complicated definition of work, which is the work-energy theorem. Work is the change in potential energy plus the change in kinetic energy. What's change in anything? Mr. Dewick, the reason you went on that big rant earlier in the year, is it because you knew this was coming down the pipe? Yes. So what's change in anything? Okay. So this is really work equals potential energy final minus potential energy initial plus kinetic energy final minus kinetic energy initial. Now we need to jog our memories, because normally I get through this in one lesson and I've had to split it up. So once you write that down, stay where you are. I'm going to scroll back. Potential energy was mgh, where h stood for height. Aiden, read the question. Is there any indication in the question that there is a change in height? Does it mention a ramp or anything like that? No. So you know what my change in height is? As a number exactly? You know what my change in potential energy is as a number exactly? So because it's level ground, I can actually either have crossed this out or I can cross that out. But I wanted to show you that they are both final minus initial, so this one time I wrote them out. Okay. Also, kinetic energy, this was our new equation. Can you find it from your formula sheet? How do I calculate kinetic energy? You're going to end up memorizing this one. It's that important, but for now, you need to know where it is on your sheet. How do we calculate KE? How do you think I calculate KE final? A half mv final squared. How do you think I calculate KE initial? A half mv. Fair enough? Yes? So this is going to become a half mv final squared minus a half mv initial squared. Aiden, I would underline this word. What's that tell me? Stop. I don't mean stop, sorry. What does the word stop tell me, Aiden? Yes? Okay. So now I can plug and chug. It's going to be negative 0.5 m 1200 v 32 squared. You're going to get a negative answer. What's the negative telling you? If the car is traveling forwards, which way is friction acting to bring you to a stop? It's telling you the force and the distance are in opposite directions. It's also telling you the car needs to lose kinetic energy to come to a stop. You're going to get a big answer. Pretty sure. What'd you get? Read me the digits. Negative what? That? Okay. Yeah. By the way, what if you were going twice as fast? How much more energy would you have? Nick, loud and proud. What? Okay, here's what else that means. It takes you 4 times the distance to stop if you're going twice as fast. Not twice the distance. What if you're going 3 times as fast? How much more energy would you have? What's 3 squared? 9 times the energy. And by the way, that means it'll take you 9 times further to stop if you're going 3 times as fast. I've just explained about half of the car accidents out there. People don't realize this. If you're going twice as fast as you usually do, it's going to take you 4 times further to come to a stop. It has nothing to do with how good a driver you are. It's physics. If you're going 3 times over the speed limit, it's going to take you 9 times further to stop than you're used to. Nothing to do with your driver's skill level. It's that squared. That squared dominates your life in ways you can't even imagine. I'm going to go on many a rant about that squared. And I'm hopeful that for many of you, that squared will also come to bite you in a way that will just make me laugh hysterically. But that's a preview of coming attractions. Okay? So, the car needs to, by the way, I read that as, the car needs to lose 614,400 joules. The negative tells me the car's got to get rid of the energy. Where's that energy going to go? Heating up the brakes, probably. When you stop, you generate a lot of heat. Okay? Example 9. An artillery shell is launched from a cannon. At the top of its arc, it reaches a height of 245 meters with a horizontal speed of 95 meters per second. What's the minimum amount of work that the cannon did on the artillery shell? Okay. This is an arc. This is a parabola. But the nice thing is, because work is a scalar, no t-table. No ax, no ay, no components. What's this question Connor asking me to find? How much what? What is the minimum amount of work? My first thought, don't write this down, would be force times distance. Now there is sort of a distance, a height, but there's also a speed. I don't think it's force times distance. My second thought would be, hey, is there a force versus distance graph? Because in the same way that we figured out how much work to move an object from 2 to 6 meters, we could do that. Is there a graph? Be obvious, Connor. Did they give me a graph? So my third, better but more convoluted definition of work. Work is the change in potential plus the change in kinetic. Usually when I write this one down, I pause and I ask, are any of these 0? What I normally would have done, for example, 8, is I would have said, is the change in potential energy 0? Is there a change in height? No, 0. In this question, is there a change in height? Yes. So not 0. Is there a change in speed? Yes. What's the projectile's initial speed while it's on the ground before we pull the trigger? What's its final speed, apparently? Maximum speed, 95. So both of these are not 0. Karn, what's changing anything? So this is going to end up being PE final minus PE initial, and then a plus sign. KE final minus KE initial. What was the equation for kinetic energy? It's on your sheet, folks. So you need to look. That's what I'm really saying. So no blank staring at me. What I'm really saying is go look on your sheet. How do I write KE? So I'll leave a space. This is going to be plus a half mv final squared minus a half mv initial squared. What's the equation for gravitational potential energy on your sheet? I hope, think. What's PE? On your sheet? Is it not on your sheet? Better be. Okay, then let's not have that 30 seconds of silence. We've got to participate here. What is it? What do you think PE final then is going to be? MGH final. What do you think PE initial is going to be? MGH? Okay. Are any of these 0? What's my final height? Read the question. Not 0. What's my initial height? I think we're going to assume we're starting on the ground, which will be a height of? Oh, okay. What's my final speed at the top, or maximum speed? 95? What's my initial speed before I pull the trigger? How much work did the cannon do? Did the cannon do on the cannonball? Or let me phrase it differently. How much energy did the gunpowder transfer to the shell? Because that's really what we're doing now with work. We're saying that's an amount of energy, because energy is the ability to do work. How much gunpowder would I need to use? You could actually calculate that if you knew how much energy there was per liter of gunpowder, per pound of gunpowder, per kilogram of gunpowder. Let's find out. What's M? What's G? And positive, because we're in scalarville here. Don't need to worry about a negative 9.8. What's H? 245. Minus, plus 0.5. What's M? What's V? 95 squared. By the way, 19 kilograms, that's around, actually that's heavier than the mass that I was holding over Aiden's head. So cannonball. And 95 meters per second, pretty fast. 245 meters, pretty high. You're probably going to get a pretty big answer. What do you get? Do you get 13135? I'll call it 131,000. I'll go to 3 sig figs. Okay. Look up. So here's the artillery shell. Here's what's really happening. Boom, we pull the trigger right there, and it's got 131,000 joules of energy. All of that right at the beginning is all kinetic energy. It's the energy of motion. In fact, I could figure out how fast it must have left the ground at. I could take that 131, I could take that number there, and I could times by 2, divide by m, square root, I'm getting the v in the half mv squared by itself. It left the ground at about 117.6 meters per second. Boom. That was enough for it to reach a height of 245 meters while still having enough kinetic energy to be traveling that way at 95 meters per second. So as it gets higher, it's losing kinetic energy, slowing down, turning that into the energy of height, potential energy. If we had fired it straight up, I could actually figure out if we fired it straight up how high it would go, because at the top for a split second, what would its velocity or speed be? So how much kinetic energy would it have? 0. It would all be potential energy. I could figure out how high, if I pointed it straight up, it could go. And not a T-table in sight. Scalarville. The tricky part, Noah, is this is all brand new to you. This would be way easier if this was a review lesson like the first lesson of forces when I was reviewing Newton's laws, and instead of going, what, like you were last year, you're going, oh yeah, I remember all that. So we're doing a little cold turkey. Don't worry, we'll figure this out. I bet you I'm going to use a force versus distance graph here, just speculating. Okay. I like example 10. I like example 10. Example 10 is a nice question. Allie, what's example 10 want me to find? Keep reading. Keep reading to yourself. And eventually, if you look underneath the graph, you'll see the question sentence. And then you'll say, what's it want me to find? Yeah. One of the things you're going to notice is you'll never, at least you shouldn't, ever see me use the word velocity. I'll use the word speed or how fast, because we're in Scalarville right now. Velocity, magnitude, and direction. Speed, scalar. What's it want me to find? How the heck am I going to do that? What kind of a graph is this? What's on the y-axis? Force in newtons. That's not normal force. That's not an F subscripted N. That's, I'll always put the units on a graph because I'm a nerd. What's on the x-axis? Hey, this is a force versus distance graph. You know what the area underneath the force versus distance graph is? Work. See how that long chain of reasoning? Okay. What's it want me to find? Okay, this is going to sound really strange, but I'm going to start out by writing this. Work equals work. What? I know that's kind of Captain Obvious. But then I'm going to put the two definitions of work. What's the first one? The WorkEnergy Theorem. What is the WorkEnergy Theorem from your formula sheet? Okay. The fact that many of you haven't looked at your formula sheet yet is starting to bug me. So Allie's going to look at his formula sheet and he's going to find where the WorkEnergy Theorem is. It's on there. It's called the WorkEnergy Theorem. Yes, I think? It's not labeled? Did I not? Hang on. I got to confirm that. Allie, what's the longer definition of work, the WorkEnergy Theorem? Can you read me that equation, please? W equals. So find where it says, huh? The long one can't go, Allie, can't go force times distance because that only works for a constant force. Here we have a changing force. So read me, this is the WorkEnergy Theorem. This is today's lesson. Read it. Keep going. What does PE stand for? Potential energy. Okay. Keep going. Okay, there's one. Equals, you know what the other definition of work for this question is? Area. Okay. Now, why did I do that? Allie, what were they asking me to find? How what? Psst, psst, look up, look up. Isn't there a V hidden in there somewhere? A fast? Yes. That's how I knew to do that. Is there a V hidden in force times distance? No. So, okay. Change in potential would be if there was a change in height. This is a forward distance, not a height. So everybody cross that out. If I gave this to you on a test, Noah, I would include the phrase over level ground. I would make it clear, and I forgot to for this question. I'll change that. What's change in anything? So the left-hand side can be written as KE final minus KE initial. The right-hand side is going to be the area. Now, Allie, can you read to me the whole question, starting with how fast? Can you read to me the whole question, starting with how fast? Starting with how fast? You have it on your sheet in front of you, right? So read it from there instead of squinting and trying to read it from up here. Starting with the word how fast. Start with the word how.
How fast it's traveling after 0.8.
After what? After what? After what? On our graph, let's draw a little vertical line right there. Okay. Sorry for picking on you, but got to work our way through this. Do you know what the area is? It's going to be this. What shape is that? Hint, not a trapezoid. What's the area of a triangle? Now, if you've forgotten, I did put that one on your formula sheet. Probably where the picture of the triangle is, somewhere. And I usually, instead of writing half base times height, you may notice if it's a single fraction, I write it as base times height over 2. Okay? So this is going to be base, I'll do it in red because I wrote the area and colored the area in red. Base times height over 2. Okay? With me? Yeah. Let's calculate the actual area. How long is the base of that triangle? Read it from the graph. How long is the base of that triangle? 0.8? What's the height of that triangle? I scrolled down. You'll have to read across. Is it 16? Is that correct? Divided by 2. I'll crunch that on the next line, but yes? What about here? Are any of these zeros? Okay. And what's the equation for KE, for kinetic energy, for the energy of motion? Allie, what did this question ask me to find? There it is. Now, it's funny because we've only written a couple of lines, but can you see we had to do about 8 steps of linking different pieces of information with the concept of work, because there's 3 ways to find work. It's force times distance, doesn't help me here, but it is the area underneath the force versus distance graph, and it's also the change in potential plus the change in kinetic. Okay? I did not include work equals the area under a force versus distance graph on your formula sheet. If you wanted to add that as a note to your purple sheet, you could, but I won't let you put it on your yellow sheet. I'm going to expect you to clue in. And I think it's reasonably obvious. Geez, he gave me this strange graph. Oh, it's a force versus distance graph. What is the equation for force for work? The first equation for work, by the way. I figure the fact that it says force times distance and area does mean kind of multiply. I think that's enough of a hint. Okay. What is 0.8 times 16 divided by 2? Sorry? 0.4 even? Oh, 6.4. That equals 0.5 mv final squared. Okay, we've never done this, but how would I get the v by itself? More specific. By the way, never divide by what or do what? Divide the v final squared. Would that get it by itself? I think I want it to stay here. So what do I want to move over? The 0.5 and the... What are the 0.5 and the m doing to the v squared? So I'll move them over. Oh, we've seen this before. Vf squared. Well, I've scrolled down. What was the mass as a number? The question must have told me, I hope. Sorry? Okay, so final speed is going to be the square root of 6.4 divided by 0.5 times 25. Square root. You get 0.7155? So 0.716 if I go to 3 sig figs? Meters per second? Just making sure all my numbers were right. Yeah, 0.716. So here is yet another way to find a final speed. I don't know how many we've learned over the past year and a half, but a bunch. When would I use this one? Well, specifically if they gave me a force versus distance graph, but really you're going to see, I would use a method something like this, the work energy theorem, if there's a curvy path. And there's no way to do easy components. But did we do components? It's a scalar. Okay? So that was the finish of the lesson. So here is your homework, and I know you're also studying for a test, but you have tomorrow afternoon off. I see you tomorrow morning. We're going to be doing lesson 2 tomorrow morning. Also take tomorrow, you want to come prepared for any questions about forces. Y'all got, I emailed out a forces tutorial on YouTube to you as well. Okay? I will be in tomorrow afternoon if you want to just come here and ask questions about forces. I'll be here tomorrow. For now, though, what's your homework? Number 1. It says write a work energy equation. I think you're going to use change in potential plus change in kinetic. How did I figure that out? Because there's a speed in part B, and kinetic is the one that has speed in it. Okay? We're going to assume that you're throwing the baseball horizontal. Oh, it does say horizontally. If you're throwing it horizontally, is there a change in height at all? No? That's why it says work equals change in kinetic. It doesn't say change in potential plus change in kinetic, because the change in potential is 0. So number 1, try that. 2B. For A and B. Can you all look up for a second? I think for 4A, you can actually do that because I don't see a hill mentioned in this question at all. So there is no change in height, so no change in potential. So you can just use change in kinetic. In fact, I think it's very similar to the car question that we did where we got a pretty big answer. You'll get a negative answer. I didn't include the negative in my answer because it just said, what's the net work done? You lose that much energy, but you'll get a negative answer, I think. 5 is good. 6 is good. 7 is good. 8 is good. 9 is good. 13, I see a force versus distance graph. And 15. this is the first time I've done work cold turkey in Physics 12, so if you have questions, blame me. I'm trying to gauge how fast I can go. I took a Physics 12 lesson and I kind of added more intro to it, so I don't know how well that one went.